Topic 4.3, which regression model, linear or quadratic, based upon the context of the data's variables, meaning like the context of the actual question, can most reasonably model the data set? So here you're just sort of using intuition and you're using your brain to be able to think about the situation that's being described. In this case, if you remember, it's tip amounts being left according to a certain bill at a restaurant, and trying to match features of linear and quadratic functions to something that would reasonably happen in the data set. Okay, so these are my questions. Of the two regression models previously analyzed in the problem above, which model, linear or quadratic, is more reasonable to model the data and explain your reasoning? So which one is more reasonable? And then are there any limitations to the model you chose? So if you remember, this is our linear model, this is our quadratic model. These are the graphs, bill along X and then tip amount along Y for both. So first, let's take a look at some features of linear and quadratic functions that you could use to match in a description. So the first feature is the shape of the function. Linear function's shape, right, is a straight line. It's a positive slope or a negative slope linear function, and what that means is that as the independent variable increases, the dependent variable is just increasing or decreasing at a constant rate. Quadratic function. Those are either concave up or concave down. They're defined by a parabola. These functions, as the independent variable increases, right, the dependent variable first either decreases and then increases, or increases and then decreases. So that's called the shape of these functions. Always increasing, always decreasing, decreasing and then increasing and decreasing. Okay, the next thing that are different from linear and quadratic functions is something called the average rate of change. Now, the average rate of change is so you can apply to all functions. We looked at the rate of change previously for linear functions, and we call it the rate of change because it's constant across a linear function. It's up 1 over 1 or up 1, right 1 for y is equal to x, and right 1, down 1 for y is equal to negative x plus 4 across this entire function. So this rate of change is constant. It's always going to be this plus 1 or plus 1 minus 1 for this graph here, a constant rate of change. Quadratic function's average rate of change, though, is different across the graph. This quadratic function goes up 1 or right 1, up 1, but then as it goes right 1 again, it goes up 3. So this change is different. For every 1 you go over, first it goes up 1, but then you go over 1 again and it goes up 3. Same thing for this one down here. For every 1 you go over, first it goes down 1, but then you go over another one, it goes down 3. So the difference between, you could say, dates in the context or time in the context of an actual regression model would be that as time increases steadily, things are either increasing or decreasing rapidly, more rapidly. So that's the average rate of change not being constant and either increasing or decreasing. So these are two features, the shape of a graph and the average rate of change you can use to describe the data set in context. So first, the linear. Basically, you could say as the independent variable increases, the dependent variable increases at a constant rate. So if you can describe the data set in context like that, then you can say that about a linear model. How about independent variable? As the independent variable increases, the dependent variable decreases at a constant rate. This one down here. So if either of these two apply to something that's happening in really real life that you're taking data from, you could say a linear function is good for this data set. Quadratic, if something increases, right, and then decreases at a non-constant rate, and that can describe something that's happening that you're collecting data from, you might say that it's quadratic. Or increases, as the independent variable increases, the dependent variable first increases and then decreases instead of decreases then increases. Right? So if these kind of independent and dependent variable relationships are matching your data, then you could say, all right, linear is better, increasing at a constant rate or decreasing at a constant rate. Quadratic is better. This data kind of looks like it decreases and then increases, or this data kind of feels like it's increasing then decreasing. All right, so let's go back to this restaurant owner tipping situation. So the two regression models previously analyzed in the data above, which is more reasonable to model the data. I'm saying quadratic. Quadratic did have the greater coefficient of determination. But really, you can make an argument for each one, and we'll see that in a moment. So I'm saying the quadratic model. But you're just basically choosing either model, linear or quadratic, just trying to use mathematical reasoning. To me, it makes sense that it's the quadratic model. And here's why. So here's when you explain your reasoning, you basically are trying to say, how does the feature of the function type match the data? So this statement does. So I chose the quadratic model because an increasing rate of change in this context represents higher and higher percentage tip amounts as the total value of the bill increases. This makes sense because wealthier patrons that can afford higher bill amounts may be generous with their tipping. So kind of like the more money that you have, the more you can afford to go out, and then you're not going to be Scroogey about the tip. You're just going to be tipping more and more. Now, limitations of the model. That means like, okay, you argued for it with the wealthier patrons paying higher tip amounts, but what about an argument against a quadratic model? So this is, how does the feature of the function type you chose not match the context of the data? So you might say something like this. The limitation to using a quadratic model is that a constant rate of change rather than an increasing rate of change may be more applicable to the public at large, given that tipping exactly 50% is a widely accepted social norm, whereas generally people don't tip 25 to 50% or higher. So if you tip 25, 50%, that's like where the quadratic graph is increasing more and more, and your tipping rates are getting higher and higher. No one's going to tip 50% or a bill, so that doesn't make sense. So this is like two sides of a debate. You're explaining your reasoning to choose a certain model, and then you're saying, wait a minute, this model might not work for this reason. That's my limitations.